If you've been following the peptide and longevity space, you've probably heard about incredible compounds like MOTS-C, BPC-157, or various nootropic peptides that promise cognitive enhancement and neuroprotection. But here's the inconvenient truth nobody's talking about. Most of these peptides can't actually reach your brain. Today we're diving into the blood-brain barrier problem and the fascinating solution that's changing peptide therapy forever. Your blood-brain barrier is one of the most protective structures in your entire body. It's essentially a highly selective security system made up of tightly packed endothelial cells lining your brain's blood vessels. These cells are locked together so tightly that there's virtually no space for anything to slip through uninvited. The BBB exists for good reason. It protects your brain from toxins, pathogens, and harmful substances circulating in your bloodstream. But here's the catch. It also blocks more than 98% of all therapeutic drugs and nearly 100% of large molecule therapeutics from reaching your brain. To put this in perspective, only very specific types of molecules can cross the blood-brain barrier naturally. Small, lipid-soluble molecules under 400 to 600 daltons might passively diffuse across. Things like oxygen, carbon dioxide, and certain hormones can slip through because they're fat-soluble and tiny. But peptides? Most peptides are water-soluble, relatively large, and get completely blocked. This is why you can take a peptide that shows incredible neuroprotective effects in a petri dish, or when injected directly into an animal's brain, but it does absolutely nothing for cognitive function when you inject it subcutaneously or take it orally. The peptide never reaches the target tissue. Let's use MOTS-C as a perfect example. Research shows that when MOTS-C is administered directly into the brain, what's called intracerebroventricular injection, it enhances memory formation, protects against Alzheimer's-related proteins, and dramatically reduces neuroinflammation. The effects are profound. But when you administer standard MOTS-C peripherally through subcutaneous injection or intravenously, near-infrared imaging shows virtually no signal in brain tissue. The peptide simply cannot cross that barrier. You're getting fantastic systemic benefits for metabolism, insulin sensitivity, and muscle function, but zero cognitive or neuroprotective effects because the blood-brain barrier is doing its job too well. This creates a massive problem for peptide therapy targeting neurological conditions. How do you deliver therapeutics that could genuinely help with neurodegenerative diseases, cognitive decline, or brain injuries when the brain's security system won't let them in? For decades, this was the bottleneck in central nervous system drug development. Brilliant compounds that worked beautifully in every other organ system were useless for brain disorders. The solution? Cell-penetrating peptides. These are short amino acid sequences, typically 8 to 30 amino acids long, that have the remarkable ability to cross cellular membranes and, crucially, traverse the blood-brain barrier without compromising its integrity. They essentially act as molecular shuttles, carrying therapeutic cargo across barriers that would otherwise be impenetrable. The discovery of cell-penetrating peptides started somewhat accidentally in the late 1980s, when researchers studying HIV found that the TAT protein from the virus could enter cells with remarkable efficiency. Since then, over 2,000 naturally occurring and synthetic peptide sequences have been identified with cell-penetrating properties. But here's what's critical. Not all cell-penetrating peptides are created equal, and good cellular uptake doesn't automatically mean good blood-brain barrier penetration. Research comparing different cell-penetrating peptides found dramatic differences in their ability to cross the blood-brain barrier. Some of the most effective BBB penetrating peptides include TAT 47 to 57, which shows an influx rate of 4.73 microlitres per gram per minute. SynB3, derived from antimicrobial peptides, shows 5.63, and pVEC demonstrates the highest penetration at 6.02 microlitres per gram per minute. Meanwhile, other peptides like the transportin analogues show negligible to low brain influx, despite excellent cellular penetration in other tissues. For MOTS-C specifically, researchers screened various cell-penetrating peptides and identified one called PRR5, that's 5 proline arginine arginine repeats, as particularly effective. When they conjugated MOTS-C with PRR5 to create what they call MP, the modified peptide successfully crossed the blood-brain barrier when administered intranasally or intravenously. Brain imaging showed strong fluorescent signals throughout brain tissue with the MP conjugate, whilst unconjugated MOTS-C showed nothing. The mechanism these peptides use is fascinating. Most cell-penetrating peptides cross the blood-brain barrier through something called adsorptive-mediated transcytosis. Because many of these peptides are positively charged, cationic, they interact with the negatively charged components of cell membranes. This triggers the cell to basically engulf the peptide in a small vesicle, transport it across the cell and release it on the other side. Other peptides use receptor-mediated transcytosis, hijacking specific transport systems that normally ferry nutrients or other molecules into the brain. The characteristics that make peptides effective at crossing the blood-brain barrier include small size, few aromatic residues, hydrophobic nature, and slight cationic charge. These properties allow them to interact with membranes without disrupting barrier integrity, whilst still achieving transport across that formidable obstacle. So what does this mean practically? If you're using peptides for cognitive enhancement, neuroprotection, or treating neurological conditions, delivery method and formulation matter enormously. Standard peptide formulations administered subcutaneously will provide systemic benefits, but limited to no brain penetration. For central nervous system effects, you need either direct intranasal delivery with appropriate formulation, or peptides specifically conjugated with validated BBB penetrating sequences. The future of peptide therapy for brain health lies in these peptide drug conjugates. Therapeutic peptides chemically linked to BBB shuttle peptides. This technology is already being applied to deliver chemotherapy drugs for brain tumours, gene therapies for neurodegenerative diseases, and neuroprotective agents for conditions like stroke and traumatic brain injury. We're essentially tricking the brain into accepting therapeutic molecules it would normally reject. For compounds like MOTS-C, the MP conjugate represents a genuine breakthrough. It maintains the metabolic and longevity benefits of standard MOTS-C whilst adding legitimate cognitive and neuroprotective effects through actual brain penetration. But here's the reality check. These modified versions are currently confined to research laboratories. The MOTS-C or other peptides you can purchase through various channels are standard formulations that won't meaningfully cross the blood-brain barrier. Understanding the blood-brain barrier problem is essential for anyone serious about peptide therapy. Not every peptide needs to reach the brain. Systemic effects are valuable and legitimate. But if you're specifically seeking cognitive enhancement or neuroprotection, you need to understand whether your chosen peptide and delivery method can actually reach the target tissue. The science of peptide delivery is advancing rapidly, and cell-penetrating peptides represent one of the most promising strategies for overcoming the blood-brain barrier challenge. The barrier exists to protect you, but with the right molecular keys, we're learning how to unlock its potential for therapeutic intervention. That's the future of peptide-based neurotherapeutics,